with the talk of Maycol from Universidad Federal Fluminense. He will be discussing positive neighborhoods of manifolds. So, thank you very much.
Okay, so thank you to the organizers for the invitation. Estoy muy contento de participar es un honor para mí participar de esta celebración a Fernando que siempre me recibió muy bien en Buenos Aires, participar del seminario y de las celebraciones después del seminario. Espero que continúe organizándolo por mucho más tiempo. So, I'm going to talk about manifolds, neighborhoods of manifolds with ample normal bundle. Okay, so this is a work with Fran Loret and Georges Vittorio Pereira. And as yesterday, we consider a manifold, not necessarily compact, just a neighborhood. Okay? And why a compact connected submanifold? So we are going to talk about neighborhoods. We consider X and Y, compact submanifold, and we want to understand the neighborhood of manifold. Okay, so our object will be the field of germs of meromorphic functions along the manifold. So this is a field. Okay. So we consider convergent functions, meromorphic functions, defined in a neighborhood, maybe smaller, but containing Y. Okay. And the natural question is how many functions I can have in this field. So we have the theorem of Andreotti and Harshon that says that when the neighborhood is positive in the sense that the normal bundle is ample, then the maximal number is the dimension of X. Okay? And so this is the theorem. Over C is equal or smaller than the dimension of X. So for example, if we consider curves contained in surfaces, we can have maximal 2 meromorphic functions, independent meromorphic functions. Okay? So I will give some examples. Okay? The first example is the case of curves in a projective surface. So in this case, if S is projective in the sense that is contained in some projective manifold, okay, then we have that the transcendence degree is 2. Of course, in the case of a positive curve, I mean, this is a curve, in this case, in this example, with positive self-intersection. Okay? So, in this case, when it's projective, we have 2 meromorphic functions because we can restrict the rational functions on the surface S. Okay, so it's a necessary condition, the projectivization of S, okay, to have 2 meromorphic functions. But this is not the only case when we can have 2 meromorphic functions. So now I'm going to give an example with 2 meromorphic functions, but not algebraic, not a projective surface. Okay, so this is a ramified covering over the diagonal. So I take the diagonal in P1 cross P1. This is a rational curve. Okay. This is a rational curve. with self-intersection equal to 2. Okay? Of course, I have two meromorphic functions here, two rational functions in the neighborhood. For example, I have these two fibrations, the horizontal and the vertical fibrations in the neighborhood. Okay? And then we take, let me see. Then we take the 2-to-1 ramified covering, ramifying here over the diagonal. Yes? So I have a rational curve, a neighborhood of a rational curve, C. Now the self-intersection of C is 1. Okay, C is still rational. Yes. This I call S, this neighborhood. Okay. And when, we can see that the two fibrations here, when we pull back here, we obtain two foliations that are transversal to the curve. Okay. Two fibrations again, but they are tangent along the curve. Okay. This we can see locally. Okay. So the claim is that this neighborhood is not algebraizable in the sense of projectivity. It's not algebraizable. This is the second example. Okay? So how can we see this? So assume that it's algebraizable. Okay, assume that C is contained in S in some projective surface. So we can see that this neighborhood, in this case, is equivalent to the neighborhood of a line on P2. I mean, it's a linear neighborhood in this case. Okay? So we have a line on P2, and each fibration here is defined in a neighborhood of the line, and it can extend to all P2. Okay? So extends as a foliation on P2, totally transversal to the line. So it's a degree 0 foliation. It's a foliation by lines with a radial singularity somewhere. Okay? Like this. And this is true for the two fibrations. So I have two degree 0 foliations. And we know that for 2 degree 0 foliations, there is always a common leaf that is the line passing through the 2 points. This will be a common leaf. So this will be the tangency locus between the two foliations. And this is not possible in our configuration. Okay, because here the tangency locus is exactly the curve. So this is not algebraizable. We have our claim. Okay? This is the second example. So it's an example with, of course, here I have two meromorphic functions because I have two fibrations, different foliations. Okay? In this case, the transcendence degree is also 2, but is not a projective surface. Okay? This is the second example. And the third example is a theorem with Frank Lohe, where we give for every positive number a neighborhood of a rational curve with self-intersection D and with no meromorphic functions. Okay? So the third example, I will give an idea how we do this. I will give an idea of the construction of these neighborhoods. So we take two trivial neighborhoods of P1. Okay. Here I have a disk times P1 and a P1 times a disk. So these are trivial neighborhoods. Here the self-intersection of the curve is 0 in each neighborhood. And we glue these two neighborhoods in a neighborhood of some point by a local isomorphism. Okay, we glue here with this part, and we obtain a surface containing two copies of P1 with 0 self-intersection. Okay, we obtain a surface, and then we blow up this point, the intersection point. Okay, so we obtain configuration like this. Now the three curves have -1 self-intersection, so they are exceptional, and we can contract these two curves, 2 points now, and we obtain our neighborhood. This is a +1 neighborhood. Okay, this is C, this is S, and of course the field of meromorphic functions is the same because they are birationally equivalent. Okay, and the important part here is to choose this phi in order to have no meromorphic functions. In fact, we prove that there are no foliations in this neighborhood, okay? Because a meromorphic function here is rational in this coordinate, in the first coordinate, is global, is rational, and here is rational in the second coordinate. So we choose the isomorphism such that any meromorphic function here pass through phi to a meromorphic function here. This is the idea. Okay, so we obtain the surface with 0 transcendence degree, okay, with no foliations. So in collaboration with Georgi and Frank, we give a more general construction. I mean, here I have 2 and 0 meromorphic functions. Of course, we ask if there are neighborhoods with 1 meromorphic function, just 1. Okay, and in fact we do this for any dimension. Okay, this is our result, our main result, and okay, so we have 2 numbers who has a projective manifold, and 2 numbers L and M. L will be the transcendence degree, the number of meromorphic functions. M will be the dimension of the neighborhood. Okay, and we say that we can obtain any transcendence degree between 0 and the maximal number that is M, the dimension of the neighborhood, if the codimension of the variety of the manifold is big enough. Okay, this is for big codimension. Then there is a germ of a smooth manifold with dimension M containing Y with normal, with ample normal bundle and with L meromorphic functions. Okay, this is our theorem, and I will give the idea how to do this. But I want to say that this is not true if the codimension is not big. For example, Rossi shows that if the codimension is 1 and the normal bundle is ample, we have always the maximal number of meromorphic functions in the dimension at least 2, if the dimension of Y is at least 2. So this is not true for curves. Okay? Okay. So I will give the idea, the steps, and a sketch of the proof of this theorem. So I will do the case of Y a curve of dimension 1, okay? And I will we will construct a surface containing a curve with the correct number of meromorphic functions. So the first step is to embed. We take an embedding of the curve on P3. Okay? And then we consider a foliation by curves, F a foliation by curves. On P3. Okay? And of course, we have the curve here. I have a foliation by curves in P3. Maybe it has tangencies with the curve. Okay? And the first step is to move the foliation in order to be totally transversal here. Okay? We apply automorphism of P3 in order to be transversal with the curve. This is the first step. For general automorphism, we have that the pullback, the translate of the foliation, is transversal in the wake sense. Transversal, I mean that the tangent spaces are different, okay? Because this is a foliation by curves, this is a curve. Of course, they are not transversal in the strong sense that they span all the tangent space of P3. They are just different. Okay, and this is an application of Clayman transversality theorem. How we do this? We take the lift, we consider M, the projectivization of the tangent bundle of P3. This is a variety of dimension 5. Okay, and here we consider the lifting of the curve. I mean, for each point, we consider the tangent space of the curve, and this is a point here. So we have a lifting in M, I call it C tilde. This is the projectivization of the tangent bundle of C. Okay? And we can also lift the foliation. For each point, okay, we can lift the foliation. I obtain a surface S associated to the foliation. This is just, we take the point and the tangent direction of the foliation over the regular points. And then we take the closure. Okay? This is a variety of dimension 3. Okay, this is dimension 1. This is dimension 3. And of course, the intersection of the two varieties are the tangency points. In the tangency, they correspond the same point. So, for a variety like this, point. These points correspond to the tangencies. Okay? And then the sum of the dimensions is smaller than the dimension of the homogeneous variety M. Okay? M is homogeneous in the sense that the automorphism of P3 acts on M by derivation transitively. Okay, so this is an homogeneous space, and then we apply Clayman transversality theorem, and we see that the translate of the surface is the joint of the curve. See? Transversality in this sense by Clayman theorem. Okay, and that means that if they are disjoint, so there are not tangency points. So we can assume that they are totally transversal. Okay? And then this is our second step. This is step 1. Okay? So we apply Clayman. Step 2, So we assume that is totally transversal. Again, in the wake sense, we take a neighborhood of the curve. Okay, we take a neighborhood U on P3. Okay, a small neighborhood, a tubular neighborhood, for example, of the curve, okay, where the foliation is totally transversal, and then we take the space of leaves. Okay, we project identifying all the points in the same leaf of the foliation. Okay, and we obtain a two-dimensional variety. Okay, we take P, the projection of U, to U, the quotient by the space of leaf of the restriction to the foliation, of the restriction of the foliation to U. Okay, so this has dimension 3. This is a surface, a smooth surface. Okay, I call this X. This will be X. Okay, it's smooth. And it contains a copy of C. The image of C is a copy. It is isomorphic. Okay, it's isomorphic to C. So this is C0. It's isomorphic to C. Okay, and what can we do with this? What we obtain is that meromorphic functions here in X, if we take a meromorphic germ of function, by composition with P, give a meromorphic function here that is constant along the leaves of the foliations. Okay? So we have a natural isomorphism between the meromorphic germs of functions. Okay, and the first integrals of the foliations. These are the germs of first integral of the restriction. Okay, these are germs of first integrals of the restriction. Okay, a first integral is just a meromorphic function that is constant along the leaf of the foliations. Okay? And then we have meromorphic functions here around the curve C, and we can apply an extension theorem to extend the function to a rational function on P3. Okay, this is the idea. The third step is to apply Hironaka-Matsumura theorem. Okay, these germs of first integrals are in fact rational first integrals of the foliations, of the foliation. Okay, these functions defined here extends to P3, and so we have that this field of meromorphic functions is isomorphic to the rational first integrals of the foliation. And now we just need to choose the foliation with 0, 1, or 2 first integrals. And we have the transcendence degree of this field. Okay? So this shows the theorem in this case. Okay. But this construction by foliations, by transversal foliations, does not work if the codimension is not big, okay, as we will see here. Okay, so now we will study foliations transversal to manifolds. Okay, so we take a codimension Q foliation and a manifold C, compact manifold, disjoint from the singular locus of the foliation, and the theorem with Frank and Georgi say that if the manifold is transverse to the foliation, transverse in the strong sense, they span the tangent space of Pn, then the dimension is exactly the codimension of the foliation, and SIT is a projective space linearly embedded on Pn, and the foliation has degree 0, so it's an every leaf is algebraic, so it has maximal number of first integrals. Okay? So in this case, I will not obtain other number of meromorphic functions by this construction. So I will give an idea how to prove this. Let me see. Yes, observe first, we'll give an idea of the proof. Observe that the dimension of SIT is at least Q because they are transversal with the foliation. So dimension is at least Q. Okay? And then if we consider the inclusion of, I want to consider the restriction of the foliation to SIT. Okay? They are transversal, so I consider the inclusion and the form defining the foliation. Pn, Qpn. Here I have a line bundle is the determinant of the normal bundle. I think it's the dimension of F plus n plus 1. No. Is the degree of F plus Q plus 1. This is the determinant of the normal bundle. It's a ample line bundle. Okay, this is ample. It's positive. Let me see if it's correct. Yes. And then we restrict the form defining the foliation to set. We consider this. Okay, so this is a form, a Q form on SIT. Okay. Times this bundle, okay, restricted to SIT, okay, which is still ample. So, what happens if the dimension of SIT is bigger, strictly bigger than Q? If the dimension is bigger than Q, okay? So this is a Q form in a manifold of dimension bigger than Q. So it defines a foliation of positive dimension. Okay? And this form is never 0. Okay? Nowhere 0, nowhere vanishing. Because the transversality condition. This form is nowhere vanishing, okay? Because they are transversal. This is our hypothesis. So it will define, this form defines a foliation, a regular foliation on SIT of positive dimension, And so we can apply the bound-Bott theorem, or the Bott theorem, the Bott vanishing theorem. So the normal bundle, the intersection of this bundle, Q plus 1 is 0. Okay? But this is a not trivial condition because the dimension of SIT is at least Q plus 1 in this case. And this is an ample bundle. So this is not possible in this case. Okay, this is not possible. This is a contradiction. So the dimension is exactly Q. Okay. The dimension is exactly Q. And this restriction, okay, so the dimension is Q. And this restriction, okay, and this, if the dimension is Q, this is a line bundle, okay, with an outward zero section. So it's a trivial line bundle. So this implies also that the canonical bundle of SIT is isomorphic to this negative bundle. So if the degree of the foliation is bigger than 1, this bundle is too negative. Okay, we can apply the Kobayashi-Oshai theorem. Okay, we can apply this theorem because if the canonical bundle is more negative than this number, then the variety is Pn. Okay? And the canonical bundle will be negative like this. So the degree of the foliation will be 0. Okay? We have that C is PQ, the degree of the foliation is 0, and the degree of set is 1. So it's linearly embedded. This shows our theory. Okay. What else? So we can consider also the weak transversality. Okay, let me write the definition here. So we consider a foliation as before, codimension Q foliation on Pn and sit a manifold disjoint from the singular locus, the foliation. So we say that F is weakly transversal to set transverse to set if in any point the tangent spaces are like this. Okay, for all x on set. Okay, but they do not necessarily span all the tangent space of Pn. Okay, so our last theorem is about this case. Okay. If the variety is weakly transversal, and we have this condition on the dimension, this is the complementary condition of the first theorem. Okay, this means that the codimension is not big. Okay, in particular, if the foliation has dimension 1, this is dimension C plus 1. Okay, then the foliation is algebraically integrable. I mean, every leaf is algebraic of the foliation, and so we have many first integrals, the maximal number of first integrals. Okay? Moreover, if the dimension of the foliation is 1, we can see that the degree of the foliation is 0. Okay, so I will present the idea in the last case. Okay, so I will present the proof. Is in the simpler case where the dimension of the foliation is 1. Okay, so in this case, if the dimension of the foliation is 1, we have that the condition on the dimensional condition is that the codimension of SIT is smaller than the dimension plus 1. Okay, plus 1. So in this case, we have the variety, the manifold seat, and the transverse foliation as before, weakly transverse foliation. Okay, so we can restrict the tangents bundle, the tangent bundle of the foliation to seat. Okay, and this is an inclusion on the tangent bundle of Pn to seat. And of course, we have the projection on the normal bundle. Seat. Okay, so we consider this map. Okay, so this is a never zero map because they are totally transversal. Okay, so we have a map of bundles here, nowhere vanishing. So it induced a section, nowhere zero section of this bundle. Okay, nowhere zero. So the top chair class, this is a bundle of rank. The rank of this bundle is the codimension of seat. This is a linear bundle. This is a line bundle. Okay, and so the top chair class of this bundle is 0. Okay, so the chair class, the top, I mean the codimension seat chair class of this bundle is 0. And this is not a trivial condition because the codimension is smaller than the dimension of seat plus 1. So this chair class, this index, is smaller than the dimension of the manifold. So this is not is a not trivial condition. Okay, but this is only possible in the case of dimension 1. We have that the cotangent bundle of S is OPN the degree of F minus 1. Okay? So this is sample. So this must be negative because the tensor product is not ample. It has 0 chair class. Okay? So this implies that this number must be 0. Okay? So the degree of the foliation is 0. And then, in this case, we have many meromorphic functions defining the foliation. Okay? Thank you.
Thank you very much. Questions, comments? Anyone?
I think there you can say something more because you get the normal bundle of Z twisted by -1,
Yes.
and that's always globally generated, but the top chain class is 0. So maybe you can say something more over Z.
Over seat?
Yeah.
Ah.
The normal bundle twisted by -1 is always globally generated. So when you have a
Yes.
globally generated vector bundle with top chain class equal 0, this is not...
No, but the normal bundle is global.
For every projective variety, n-1 is globally generated.
Yes.
But now you have an extra condition that the top chain class is 0. So this is maybe reflects something on Z. This is the idea.
Okay. Okay, I don't know. Maybe.
Okay, it's just an idea.
Yes, yes. No, okay. Thank you.
Any other question? Well, thank you, Michael.
Okay.